8 amazing facts that will change your view of the universe. Hello everyone and welcome to my channel. From the tiniest bends in spacetime to the vastest clusters of supergalaxies, from the throbbing of particles to the devouring of large galaxies, every detail of the universe reveals breathtaking mysteries. What is even more shocking is that these seemingly cold laws of physics are like an invisible conductor, precisely manipulating every pulse of the universe, molding chaos into unspeakable wonders. All this is no accident, but a great truth hidden deep within the universe. Today, we reveal 8 amazing facts that will change your view of the universe. 1. Cosmic dark current. Did you know that in our widely understood and familiar universe, there are still many mysteries that we have yet to understand and answer? One of these mysteries is the dark current, an amazing phenomenon. Our vast galaxy clusters are like ducks in space, guided by an unseen hand across the cosmic pond. It sounds incredible, but scientists have actually observed this phenomenon in our universe. First, let's talk about what a dark current is. Simply put, a dark current is a mysterious force that is driving some clusters of galaxies in a particular direction in the universe. Imagine if you saw a flock of birds flying in the same direction, no matter if it's raining or windy, you'd surely wonder what force is guiding them, right? That's what scientists are wondering about dark currents. Here's what scientists have discovered. They've noticed that certain clusters of galaxies seem to be moving toward a mysterious attraction point in the universe. It was as if a cosmic magnet was there, attracting the clusters. But what's most troubling is that this phenomenon seems to violate the principle of cosmic isotropy. From existing theories and observations, we originally expected that the universe should be isotropic, meaning that no matter which direction you look, the structure of the universe you see should be similar. However, the emergence of the dark current has broken this common sense, not according to the rules of the game. Clusters of galaxies are clustering in a particular region, and it's almost as if they're revealing clues to a deeper cosmic secret. A scientist named Kashlinsky was the first to point out this phenomenon in his 2008 study. He and his team analyzed the movement of distant clusters of galaxies and found that these clusters were migrating in a common direction, which is called dark current. You might wonder why such a dark current exists. Well, that's a good question. No one has been able to give a definitive answer yet, but there are several theories. Some theorists speculate that there may be some huge mass hidden behind the universe that we have yet to detect. Big mass means big gravity, which could explain why clusters of galaxies flow in certain directions. Another exciting theory is the multiverse. That is, our universe could be just one of many universes in a multiverse. If there are other universes, and they interact with our universe in some way, then the forces of those interactions could be the forces observed in the dark current. It's like an external gravitational force coming from a neighboring universe that we can't see. It's an unknown cosmic-level interacting force with effects beyond this universe we are in. There are also some scientists who believe that the dark current may be related to the distribution of dark matter or dark energy. As we know, dark matter and dark energy dominate the universe, but how they affect its structure and development remains the big question. Perhaps, dark currents are a manifestation of the influence of these dark components. These theories are still hotly researched and debated, and there is a lot of controversy, such as that of Alexander Kashlinsky of NASA's Goddard Space Flight Center, who led a study to track dark currents. Their study showed that the dark current extends farther than initially reported. Kashlinsky said, "It's not what we were initially looking for, but we can't make it go away." This suggests that the existence of the dark current may be even more complex than the universe as we currently know it. So what are its implications for large-scale theories of the universe? Our current understanding is that after the Big Bang, matter was essentially evenly dispersed through space, a bit like putting a drop of oil on water. It would slowly and evenly spread out. But if dark currents do exist, we may need to reassess this uniform structure of the universe. Some scientists have compared the universe to a homogeneous bubble, in which the bubbles are clusters of galaxies and superclusters of galaxies, which are supposed to be evenly distributed. But if the dark current thing is real, it's like a current that pushes the bubbles together, creating lumps. This means that the universe may not be as uniform as we think it is, or at least, it's skewed in some places. 2. White holes. The concept of white holes is quite different in theoretical physics. If you compare a black hole to a big vacuum cleaner in the universe, then a white hole is a cosmic-level pesticide sprayer, meaning it sprays stuff. Don't get me wrong though, it's not spraying pesticides, it's spraying matter and light, which means that if there really are white holes, they're a constant supply of matter and energy to the universe. and anything that tries to enter is completely rejected. It's like a perpetual motion machine that can only go out but not in. Now, in all seriousness, the theoretical basis for white holes comes from general relativity. You remember Einstein's famous equation, E equals mc squared? His theory of general relativity introduced the concept of space-time curvature, which describes how matter affects the structure of space. White holes are actually an artifact of this theoretical solution, which allows matter and light to escape rather than be captured. This is the complete opposite of a black hole, which is a place of no return, and matter that jumps into a black hole is like falling into a hole with no bottom. But you know what the weirdest thing in the world is? So far, we don't have any solid observational evidence of white holes, which leaves a lot of astrophysicists scratching their heads. For example, there's a big guy, theoretical physicist Stephen Hawking, who conceived the idea of white holes, and many theorists today are expanding their theories based on his ideas. And then what about how they form? This question has always been the most speculated part. Some theories say that there may be some supermassive star somewhere in the universe that instead of forming a black hole, formed a white hole at the moment of the end of its life. Or maybe they evolved from black holes. It's as if the black hole converted itself into a source of matter and light after it had processed all the matter it had swallowed. When we talk about the early universe, we have to admit that it was a very different universe than it is now. It was chaotic and wild. In the years following the Big Bang, the universe experienced rapid expansion and cooling, creating a complex physical environment. Under those extreme conditions, the creation of white holes is not so unbelievable. Some theorists, like Roger Penrose, a British physicist, has proposed a theory called conformal cyclic cosmology, CCC, which suggests that white holes could occur during transitions between different phases of the universe. And if we expand the scope and look at places that we can't see at the moment, like the far corners of the universe, or galaxies that have their backs to the Earth, there might be white holes hiding there. You can think of it as a source of light in the depths of the ocean, but until now, our submarines have not been able to dive deep enough to see it. There is also the possibility that white holes exist under very specific cosmic conditions. It's like if you want to find a flourishing tree in the desert, the conditions have to be just right: enough water, moderate sunlight, and enough nutrients. Similarly, for a white hole to appear, it may require a very specific set of conditions, such as a specific mass density, strength of the gravitational field, or some other cosmic circumstance that we don't yet know about. Scientists have said something like, much of the universe is still a mystery, and white holes are like beacons of unanswered questions standing at the boundaries of the universe, urging us to set sail and explore the uncharted waters. Remember, there was a pretty influential scientist, Kip Thorne, who mentioned in his research that white holes may have a not insignificant influence on the expansion and evolution of the universe. They may be like adding new lines and patterns to the loom of the universe, constantly. White holes are like an unsolved puzzle to us, and they may help us open new windows on the world and answer some questions about the origin of the universe and the formation of matter. Did you know that physicists have been studying the life and death cycles of stars, and the birth, evolution, and evaporation of black holes, trying to understand how they affect the pattern of the universe? White holes, perhaps, are an overlooked piece of this life cycle, not to mention how the universe maintains a balance of matter and energy if white holes really do exist and are spewing out matter as theory predicts. If white holes really are spewing out matter, that matter has to be coming from somewhere. This brings to mind the term wormhole. Have you heard of them? Simply put, a wormhole is a shortcut that connects two distant locations in the universe. Some people speculate that a white hole may be one end of a wormhole, with a black hole attached to the other end. In other words, what is eaten by the black hole may be transshipped to a white hole through a mechanism we don't yet understand, and then ejected by the white hole. Stephen Hawking, yes, the famous black hole theorist, once proposed a theory about black hole evaporation, so maybe we can draw an analogy. He said that black holes slowly lose mass and eventually disappear through a process called Hawking radiation. So if there is some unfinished business in the process of disappearance, such as the matter that it has swallowed but not yet had time to process, could it not be lost in the form of a white hole? Could be erupted in the form of a white hole? Of course, this is all hypothetical and speculative. 3. Aging stars in the universe. You've no doubt heard the story of how the universe got started, the Big Bang theory. It's not just a scientific theory, it's more like a family tree of our universe. As of today, it's still the best story we have to explain the origin and early evolution of the universe. About 13.8 billion years ago, everything in the universe, including matter, energy, and even space itself, was born out of a hot superdense state that we call the Big Bang. This state is what we call the Big Bang. It was an initial singularity of very high temperature and density, which then expanded in a flash, like a supersized fireball, and that was the birth of our universe. Then, let's move forward in time a little bit, when the Big Bang happened about 380,000 years later. At that time, the universe began to cool down, and photons began to be able to travel freely, no longer bouncing off of electrons and protons. The radiation left behind, then, that we can now see is called the cosmic microwave background radiation. It's our oldest light, and like a time traveler's snapshot, it reveals what was going on in the early universe. Through the cosmic microwave background radiation, we can see the universe as it was shortly after its birth. It's like a baby picture of the universe. As for how old the universe is, scientists have used several tricks to solve this problem. One way is to look at globular clusters, extended families of some of the oldest stars in the universe. Scientists observe the brightest stars in these clusters, measure their brightness, and then extrapolate the age of the cluster through complex calculations. Speaking of which, I have to quote a scientific heavyweight, astronomer Beatrice Tinsley: clusters of different ages and chemical compositions all have different mass and brightness distributions. In short, this is saying that different stars have their own characteristics, and that these characteristics are one of the key clues to the age of a universe. Yet scientists have actually found stars in the universe that may even be older than the universe's own birth certificate, which is a challenge to common sense, isn't it? One of the most surprisingly old stars is Methuselah, or HD 140283, an old gentleman said to be around 14 billion years old. Scientists estimate the age of the universe to be only 13.7 billion years old, which is kind of embarrassing, right? But yeah, measuring the age of stars isn't that straightforward. It involves a technique called stellar spectroscopy, in which scientists can analyze information in the light of a star to find out its composition, temperature, and so on. It's like a medical checkup for the star. For example, Methuselah has an unusually low metal content, which suggests that it was born very early indeed, since heavy elements were not as abundant in the early universe. Astronomers look at these stars with ground-based telescopes, such as the Hubble Space Telescope, or the soon-to-be-launched James Webb Space Telescope. They look at the spectra of these planets as if you were tasting the color and texture of a red wine at dinner to determine how good it is. By parsing this complex data, they are able to estimate the age of the stars and then send that data back for those of us who are curious about the mysteries of the heavens. The existence of those surprisingly old stars, like the Methuselah star just mentioned, does present a challenge to the study of the age of the universe. In dealing with this paradox, scientists first have to be able to question their methods. They would check that the observational methods are accurate and make sure that all the calculations are okay. For example, perhaps the luminosities and colors of these old stars have been misinterpreted for some reason, or perhaps the estimates of distances are wrong. But there's another key part of the story that needs to be addressed. It may touch on the fact that the standard model of cosmology is incomplete at some point. Whenever such an age paradox arises, scientists know that they may need to update or improve their understanding of the universe. Now, the discovery of these aging stars puts some question marks on the Big Bang theory and may require adjustments to the expansion rate of the universe or to the understanding of dark matter and dark energy. One possibility is that some of the processes in the early universe were more complex than we thought, and perhaps we have only scratched the surface of the cosmic timeline. Deeper secrets are waiting to be explored. 4. Dark matter bridges. When we talk about dark matter bridges between galaxies, we are actually exploring an invisible path in the universe, a bridge between galaxies. Astronomers use a variety of astronomical observations, such as the speed of rotation of galaxies, or the interactions between clusters of galaxies, to hypothesize about the unseen. It is these operations that tell astronomers the surprising truth: the gaps between galaxies are not a vacuum, but are filled with dark matter in a less obvious way. How was it discovered? By a technique called the weak gravitational lensing effect, which is used to measure the weak bending of starlight as it passes through dark matter. Scientists say it's like looking at the outside world through a piece of irregular glass. You can't see the glass itself, but you can infer the presence of the glass by the distorted shape of the view. Higher-end instruments, such as dark matter particle detectors, are also working to capture those extremely elusive dark matter particles. As for the nature and formation mechanism of these bridges, well, then again, scientists are still figuring that out. But one bold idea is that dark matter may form a spiderweb-like structure that weaves a cosmic web throughout the universe, with galaxies as if they were beads of dew on the web, linked to each other. Although the details have to be explored further, this has greatly expanded our understanding of the structure of the universe. Did you know that every galaxy in this universe, from snail-sized dwarf galaxies to grandiose giants, is born and grows without the silent contribution of a mysterious player, dark matter? It's like building a castle on an empty lot, with dark matter acting as the unseen architect and its supports, and the stars and planets we see as the bricks on which those supports are built. Scientists have observed and theorized that dark matter began to clump together in the early stages of the universe into a gel of sorts, a sort of mold for galaxies that guides ordinary matter, such as gas, into the right places. Like gas, to flow into the right places and eventually form the galaxies we see. For example, as astrophysicist Richard Massey, who works at the California Institute of Technology, discovered in a cluster of galaxies called the Bullet Cluster, he and his team revealed the truth about the distribution of dark matter by observing the bending of light in the cluster. They saw that the places where the matter was clustered didn't coincide with the actual location of the light sources in a galaxy cluster, which shouted out, "Hey, there's dark matter tugging here." So you can imagine dark matter as if it were the skeleton of the universe, which not only supports entire galaxies, but plays a key role in shaping and developing them over time. Without dark matter, the universe would probably be a pile of scattered gas, and not even a decent galaxy could be made. A famous astronomer once said, "In the drama of the universe, the stars may be the actors, but dark matter is the director." Although we have not been able to directly observe dark matter so far, we can understand the role it plays in this cosmic drama by deciphering the manuscripts of its gravity. Scientists generally agree that dark matter is the key to resolving the structure of the universe. As we've talked about before, dark matter plays an important role in both the formation of galaxies and the maintenance of the large-scale structure of the universe. But the question, what is it made of, has been haunting scientists for some time, like an ancient mystery. One of the major points of contention is what kind of unknown particles dark matter is made of. Some favor the idea of weakly interacting massive particles, others support the axion theory, and there is a wave of people who think it might be a mysterious particle that is not yet in the standard model of particle physics. Scientists argue about this, but it's also the debate that drives more experiments and research. As far as future research goes, it's really exciting. For example, in the next phase, more underground laboratories will be put into operation, specializing in the detection of dark matter particles. Meanwhile, the technology of space and ground-based telescopes is advancing, and they will provide more accurate data to verify theories about the distribution of dark matter. On the other hand, some scientists have come up with the idea of merging established physical theories with new discoveries, such as superstring theory or quantum gravity theory, which could potentially play a key role in explaining the mystery of dark matter. As celebrity physicist Lisa Randall said on a whim, the ultimate understanding of the universe may require us to redefine what matter is. It's a statement that I personally find particularly fascinating. It not only heralds progress in science, but also reveals the direction of future research, both digging deeper into the secrets of dark matter and potentially leading us into new areas of physics. The discovery of the dark matter bridge is of crucial importance for understanding the large-scale structure of the universe. As we know, the universe is not a randomly distributed desert. It has a fine structure, like a spider's web, with galaxies and clusters of galaxies distributed along the lines. Dark matter bridges, like the threads of this web, not only bring galaxies closer together, but also reveal secrets about the structure of the universe. As astrophysicist J. Richard Gott says, understanding these bridges is like reading the pulse of the universe. And then there's the particle physics connection, which may sound a bit overexpected. When we talk about dark matter, we're actually exploring those same fundamental particles that make up dark matter. You imagine that these particles are so small that we need extremely sophisticated technology to find them. The discovery of the dark matter bridge is as good as providing a clue that allows physicists to continue to explore deeper and deeper, perhaps at some unknown particle at play. This could not only help us unlock the fabric of the universe, but perhaps challenge our current understanding of the physical world. 5. The universe could be a fluid. A superfluid is actually a real state of matter that exists in our world. So, what is a superfluid? In a nutshell, a superfluid is a fluid under a quantum mechanical description that has some rather unusual properties. The most notable properties are zero viscosity and zero entropy. Yes, you heard me right, I said zero. This means that when this fluid flows in a container, it doesn't lose energy to friction, and it has zero entropy or disorder, which means that it is perfectly ordered. Let me explain this concept with an example. Try to imagine that you have a circular container filled with superfluid. Now, you start rotating this container. In a common fluid, say water, the center portion of the fluid will rotate as the container rotates, but the water at the edges will lag due to friction, and eventually the entire body of water will form a vortex in the container. However, if your container contains a superfluid, the entire fluid will instantly rotate with the container, with no lag at all, just like a rigid solid. This phenomenon was first observed in liquid helium in the laboratory, where it was discovered that at temperatures close to absolute zero, liquid helium exhibits superfluid properties. This marvelous property amazed scientists and inspired them to investigate further. Scientists conducted many experiments to detect and understand the superfluid nature. In these experiments, they discovered that superfluids have a marvelous way of transferring energy, forming so-called quantum vortices, and having strong internal coherence. Meanwhile, some theorists have tried to explain these manifestations of superfluidity using quantum mechanical theories. Now let's take a deeper look at this amazing hypothesis, that the universe may be a superfluid. During the early 20th century explorations on quantum mechanics, the physics community unveiled a layer of mystery about the universe, which directly gave birth to the concept of superfluidity. At that time, scientists had already discovered those amazing properties in superfluids, such as zero viscosity and almost zero entropy, and these properties made people think, what if some parts of the macroscopic universe also exhibit similar superfluid properties? With the development of physics, especially in the study of the two major cosmological puzzles, dark matter and dark energy, scientists have begun to search for new theoretical frameworks to explain the large-scale structure and dynamical behavior of the universe. Some cutting-edge theoretical physicists, for example, have come up with a bold hypothesis. If some components of the universe, especially those that we don't yet fully understand as dark matter, in fact exhibit a superfluid-like property, then we could use it to explain some phenomena that are difficult to explain by traditional physical models. The fascinating thing about this hypothesis is that if the universe really does contain such a component as superfluidity, then as superfluidity has shown in the laboratory, some of the properties of the universe itself, such as the expansion of the universe, the inconsistent speed of rotation of galaxies and other such enigmas, may all be explained in a completely new way. For example, have you ever wondered why the rotation of galaxies doesn't match the models we understand based on visible matter? That's because traditional Newtonian physics has trouble explaining the rotation speeds of stars at the edges of galaxies. But if you consider the dark matter in the universe as a superfluid, this zero viscosity flow property may be the key to unlocking this mystery. That's because dark matter as a superfluid would be distributed throughout the universe in an unconventional way, influencing the dynamical structure of galaxies. To go a little deeper, this theory has also spawned an emerging quest for quantum gravity. If the universe is viewed as a giant superfluid system, the quantum effects therein may manifest themselves on a macroscopic scale, providing us with clues to solving the riddle of quantum gravity. As explored by Feynman and numerous other physicists, the unification of quantum mechanics and general relativity may be hidden in such a superfluid view of the universe. Let's talk more about this theory of the universe as a superfluid, and in particular its connections and differences with familiar models of the universe, such as the Big Bang theory and theories of inflation. First, let's briefly review the classical Big Bang theory. Simply put, it tells us that the universe began in an extremely hot and dense initial state, went through a huge explosion, and then expanded and cooled to form the universe we see today. This theory has been very successful in explaining phenomena such as the cosmic background radiation, the large-scale structure of the universe, and the initial synthesis of elements. Let's talk more about the surge theory. The surge theory is an addition to the Big Bang theory, which proposes that the universe underwent a period of extremely rapid exponential expansion within a very short period of time after the Big Bang. This theory helps explain why the universe looks so flat and uniform on large scales. The bulge also explains how structure forms in the universe and why we see tiny temperature variations in the cosmic background radiation. These are the seeds of later large-scale structure formation. Now, let's look at the connections and differences between these two theories and the superfluid universe model. First of all, neither the Big Bang nor the surge theory discusses in depth the essential matter of the universe and how the microstructure of the universe affects macroscopic phenomena. The superfluid universe model, on the other hand, explores these issues from the unconventional state of matter, the superfluid state. However, unlike classical theories, the superfluid universe model offers a new perspective on how a highly homogeneous and ordered state exploded into the structure of the universe we see today. For example, the flow of superfluidity may have shaped the large-scale structure of the universe in ways that we have not previously understood. It may also provide new mechanisms for the aggregation of matter and the formation of galaxies in the universe. So, how can we use this model to explain the large-scale structure of our mysterious universe, as well as dark matter and dark energy? The cosmic superfluid model came up with an idea, saying, hey, what happens if we imagine some component of the universe, like dark matter, as a superfluid? This superfluid dark matter, because it barely interacts with light or other electromagnetic radiation, stays hidden in the shadows. But it interacts with visible matter through gravity, and may have formed this web-like structure of the universe. You know, it's like how water forms whirlpools when it flows through an obstacle, and superfluid dark matter flows through the universe and may have formed the structure of galaxies and clusters of galaxies. Now, when it comes to dark energy, that's another movement. Dark energy is thought to be the mysterious force that is causing the universe to expand at an accelerated rate. The cosmic superfluid model may give us a whole new perspective. Does it explain why the expansion of the universe is accelerating, rather than coming to a slow stop, as earlier predicted by the Big Bang model? Imagine if the mass-energy density of this superfluid could change over time and exhibit different properties at different stages of the universe. Would this explain why the universe was expanding slowly at an early stage and began to accelerate at a later stage? Some researchers are indeed investigating this possibility. They are using the hydrodynamic equations from physics, combined with general relativity, to construct mathematical models that predict how the superfluid behavior of the universe affects the formation and evolution of large-scale structures. Doesn't that sound like weather forecasting the universe? Such models can also be used to explain why the universe seems to be much younger and hotter than it should be, and why the rotation curves of galaxies don't look like we expect them to. Everything behaves as if the universe is telling us, old friend, you haven't quite figured out how I work. But then again, we need more observational data to verify that the model's predictions are accurate. If it turns out that the superfluidity model of the universe is true, it could open up a new chapter in cosmology. The theoretical model of cosmic superfluidity has stirred the pools of the scientific community because it seems to be suggesting to us new ideas for a theory of quantum gravity. First, let me explain what quantum gravity theory is. Simply put, quantum gravity theory attempts to resolve the conflict between two core physical theories, quantum mechanics and general relativity. As you may know, so far we do not have a widely accepted theory of quantum gravity. Since the nature and behavior of gravity is important on both tiny and huge scales, we need a theory that can deal with both ranges of phenomena. Imagine that the liquids we normally come into contact with, such as water, are made up of countless molecules, and that the motion of these molecules on the microscopic scale follows the laws of quantum mechanics. However, when we pull our perspective farther away, we see rolling rivers and lakes whose behavior obeys more of the laws of classical physics. Now, if we think of the universe as a superfluid, that means that at the very bottom, the entire universe may consist of some quantum mechanical elements, while the macroscopic structure and behavior exhibits classical hydrodynamic features. This hypothesis really threw up a delicious feast of ideas. Scientists began to wonder if our understanding of superfluidity could be utilized to reveal the quantum basis of the universe. That is, could the superfluid model provide some mechanism to help us understand how quantum particles behave in the curved spacetime context of general relativity? Take the example of phonons in superfluids. Phonons are quantized sound waves, and on the microscopic scale they exhibit quantum properties, like particles in a quantum field in curved spacetime. If the behavior of phonons can be somehow analogous to quantum particles in the fabric of spacetime, then the cosmic superfluid model may provide a completely new analog environment for studying quantum gravity. In addition, the superfluid theory may inspire us to rethink the nature of spacetime. In the superfluid model, spacetime may no longer be a passive arena, but an active, dynamic player. This idea coincides with some popular ideas in quantum gravity research, such as the concept of spacetime bubbles or quantum bubbles, in which spacetime is fluctuating and unstable on the quantum scale. Remember the classic double-slit experiment? Particles can pass through both slits at the same time, exhibiting volatility. Now, if we consider the entire universe as a quantum system, it may exhibit properties and behaviors we never foresaw. The superfluid model of the universe may be leading us to think in such a direction, or at least, inspiring new elements and structures that we need to consider for a quantum theory of gravity. Now, let's see what experiments and observations might confirm or refute this idea. Let's start with experiments. On Earth, physicists can create ultra-cold clouds of atoms to mimic superfluid behavior and study special phenomena such as quantum vortices in these systems. Such analogous experiments help us understand the connection between superfluid behavior at the microscopic and macroscopic levels. But how can such experiments on Earth be extended to the entire universe? Difficult enough indeed, but theories may draw inspiration from them. Now talk about astronomical observations. There are observations of large-scale structures that can be used to test the notion of cosmic superfluidity, such as studies of the rotation curves of galaxies. If the galaxies are not rotating at the same rate as we expect, that suggests an extra distribution of mass, that is, dark matter. Superfluid models can provide a new explanation for this, because we can predict the ways in which superfluid dark matter will affect the motion of galaxies. And then what about the cosmic background radiation, CBR, which we've all heard of? It's the imprint left behind by the Big Bang and gives us a huge amount of information about conditions in the early universe. Physicists have been studying detailed images of the CMB, looking for traces that cosmic superfluids might have left behind, such as specific patterns of temperature fluctuations. Existing physics experiments, oops, that's even more exciting territory. Take the best-known particle collision experiments. In the Large Hadron Collider, LHC, physicists make particles collide at close to the speed of light to recreate the conditions of the Big Bang. These experiments hope to find some new particles, perhaps including the guys who make up the universe's superfluidity. As for the cosmic background radiation, I mentioned it earlier, but it has more uses. Observations can also be used to study the rate of expansion of the universe and how that expansion affected the formation of structure in the early universe. A superfluid model of the universe has to be able to account for these observations. Otherwise, the model may have to fall back into place. How can this theory be reconciled with existing physical experiments? The key point is that it has to fit seamlessly into our existing body of physical knowledge and not conflict with the proven laws of physics. In practice, this is quite a challenge. It requires models that not only explain the puzzles we currently encounter, but also predict new phenomena that can be verified by observation or experiment. In short, we have to find the right experiments and observations that score points for the superfluid universe model, and thus help us understand whether the universe is really behaving like a superfluid. By doing so, physics can slowly get to the heart of how the universe works. 6. Cooling planets of the universe. In the vastness of the universe, there exist mysterious planets that are incredibly cold, with temperatures that are almost close to absolute zero, and furthermore, these planets are also made up mostly of ice. Yes, you heard it right, like giant blocks of ice in the universe. So, what are cooling planets? Simply put, they are planets that have extremely low temperatures and are composed almost entirely or mostly of ice. If you could stand on such a planet, the surrounding area might look like a polar ice field, but it's so much colder than any place on Earth. The characteristics of cooler planets, well, that's even more interesting. First of all, they can range in size from the size of a planet like Earth, all the way up to even more massive. But regardless of size, high density is a common feature, because water is actually quite dense when it freezes. Getting into the chemical structure, it gets much more complicated here. You can imagine, though, that in addition to water ice, cooling planets might also have methane ice, ammonia ice, and so on. Different ice types give the planets different chemical environments and appearances. Some scientists also speculate that there could be some very interesting chemical reactions inside these planets. At such low temperatures, the structure of the ice may show many interesting changes. The common ice we see in our daily lives is actually a hexagonal crystal structure, but at lower temperatures and higher pressures, ice may form other crystal structures. Scientists have discovered more than a dozen different phases of ice, each with its own unique properties. For example, a phase called Ice 7 can be stable at room temperature under high pressure. As a concrete example, a planet like Neptune, which is not full of ice on the outside but has a lot of frozen material on the inside, can give us a little bit of the flavor of a cool planet in a way. Although Neptune's surface temperature is not so low as to approach absolute zero, some of its properties, such as the composition of ice crystals in its atmosphere, give us good insights. 4 cooling planets. Imagine they were born in a very remote, sub-zero cold shivering place. It could be the outermost reaches of the solar system, or similar cooler zones away from the stars in other galaxies. There, the temperature is low enough to freeze all the gas and water vapor. The materials in these zones, such as water, methane, and ammonia, accumulate over long periods of time, gradually coming together tightly under the force of gravity, and eventually forming one cool planet after another. This is so different from our common rocky planets. Rocky planets, like our Earth, are more likely to form in hotter zones. The temperatures there allow metals and rocks to melt, and this lava then cools and solidifies, eventually stacking up to form a solid planetary surface. As for the gas giants, such as Jupiter and Saturn, they arguably grew up in a patch of relative luxury. There is enough material for them to grow into true giants in regions where large amounts of gas and dust collect, but they also have to be far enough away from the sun to prevent those gases from escaping as they are heated by solar photons. A very interesting case to study is the Kuiper Belt, where there are a lot of siblings of cooler planets, like Pluto. They form environments that are really cold. And the different water ices, or ices of other volatiles, mean that probably every cooling planet is unique. Speaking of the distribution of these cool planets, we need to talk about the Kuiper Belt and other places like it at the edge of our solar system. This is the sun's borderland, where astronomers believe a whole bunch of cooler planets are hiding. As you can imagine, because it's so far from the sun, the temperatures there are naturally incredibly low, making it an ideal home for cooling planets. Our solar system isn't the only one. The universe is huge and there are probably similar bodies around other star systems. The problem is that they are usually too small and far away to be easily observed. However, with advances in technology, such as newer telescopes and more advanced observation methods, our understanding of these distant regions is gradually increasing. Existing discoveries, such as Pluto, Eris, Haumea, and Makemake, are pretty good. These are all cooler planets found in the Kuiper Belt, which can be considered representative of known frozen worlds. They've given astrophysicists a good run for their money. After all, what a valuable resource for capturing information about the early history of the solar system. So how do scientists measure the temperature of a planet? That's where high-tech playtime comes in. Take telescopes, for example. They're no ordinary contraptions. You know, the temperature is actually directly tied to the light that an object radiates, based on an awesome law in physics called the law of blackbody radiation. So, to measure the temperature of these planets, we have to use space telescopes. Like the Hubble telescope or the James Webb Space Telescope. They can see far more than the naked eye can, and can capture the infrared light emitted by planets. The light emitted by cooler objects is in that range. Cooler planets, like these, are so cold that the light they emit is too weak to be seen by ordinary telescopes. But, with an infrared telescope, you can see the infrared light they emit. It's like the cooling planet's own little glowing labels. Scientists have been excited to study this because knowing the temperatures of cooling planets is tantamount to exploring the behavior of matter at extreme cold temperatures. These planets that survive in freezing conditions are really the history books of the universe that we have at our fingertips. They can help us explore the birth and evolution of our solar system, which is a treasure in astronomy and cosmology. You see, these planets may have preserved some of the primitive material from the early days of the solar system, and have not been subjected to much suffering from the sun. They are like refrigerators in space, and their contents are almost unchanged. Studying them is therefore tantamount to testing and improving our understanding of theories of solar system formation, i.e., we can better understand how planets gather and form. Then there's cosmic chemistry. How do the elements and molecules in the universe combine to produce all that complex and varied matter in the universe? These cooler planets provide wonderful testing grounds, giving scientists the opportunity to study these chemical processes in the universe. And perhaps most exciting of all, is the possibility of finding life. We now know that water is a key factor in the existence of life, and these planets may harbor large amounts of icy water. And who knows, maybe in some of these subsurface oceans lurks the secret of life. I remember an academic, named Kevin Hand, who came up with some mind-numbing ideas about potential life on these planets. Anyway, studying these extreme planets provides scientists with quite valuable pieces of the puzzle in understanding the big picture of the universe as a whole. 7. Zombie stars. In fact, in astronomy, zombie stars are an anomaly. They are stars that are not completely dead. Like a star that sings its last song on stage and should have retired, but instead decides to set up a little campfire and hang on to the light for a little while longer. This example might help you understand what a zombie star is. For the relationship between a zombie star and a supernova, you can think of it as a butterfly and a caterpillar. Caterpillars are supernovae, which are a stage in the life of a star and are the predecessors of zombie stars. Then, when the caterpillar undergoes a dramatic change, a supernova explosion, they become a zombie star. Supernovae are a heroic expression of the end of a star's life. During this process, the star's internal fuel is depleted, it can't sustain its original fusion reaction, and its own gravity causes it to collapse inward. When the density of matter in the center reaches a certain level, a Big Bang occurs, and even a black hole or neutron star may form. In some cases, however, the center of the star does not collapse completely, and a number of dense but still glowing stars are formed. This is what we call zombie stars. Supernova explosions have a twofold effect on zombie stars. On the one hand, supernova explosions provide the possibility of zombie star formation. Without supernova explosions, there would be no zombie stars. On the other hand, the supernova explosion also determines the nature of the zombie star. The strength of the explosion determines the mass of the zombie star, and the energy released after the explosion also provides energy for the luminosity of the zombie star. Some recent studies have shown that these zombie stars are far less luminous than they once were, but there they are, silently twinkling through the universe like bonfires that won't go out completely. Do you know what astronomers use to observe these stars? The most common ones are space telescopes, such as the Hubble telescope or the recently commissioned James Webb Space Telescope. That said, you know we have these telescopes to thank for the fine data that scientists are able to find these silent zombie stars. In research, it's all about sharp eyes and accurate data. Scientists have to analyze the light coming from the zombie stars, and they have to measure in detail the brightness, spectrum, and other properties of these stars. It's similar to solving a mystery, piecing together the truth from every clue. In the case of telescopes, the advantages are obvious. We can gain insight into the secrets of distant galaxies while sitting on Earth. But there are obvious limitations, such as cloudy weather or solar interference in the region of the sky to be observed. Moreover, these telescopes are as expensive as gold, and you often have to wait in line for months to observe any stars. One area of difficulty is that the light from zombie stars is so weak that they are swamped by brighter stars or galaxies. The good thing is that some of the optical and infrared technology is getting more and more advanced nowadays, and thanks to so many genius brains, scientists have learned how to distinguish and extract the signals they need. For example, if you're looking for a friend in a crowd of people and there's a lot of noise around you, you have to learn to hear your friend's voice through the noise. This is how scientists find the voice of the star in the cosmic noise. In the case of zombie stars, scientists characterize them in several ways, such as their mass, temperature, and luminosity. First of all, mass. In general, zombie stars are quite high in mass and density. This is because they are the remnants of supernova explosions, where most of the lighter materials have been ejected, and all that is left are some heavy elements. Then we talk about temperature. Since zombie stars are dead, their nuclear reactions have basically stopped, and they can't generate as much heat as active stars. So their surface temperatures are usually low, much lower than those of active stars. What about luminosity? Zombie stars no longer undergo nuclear fusion, so their brightness is mainly provided by an afterglow, which is slowly emitted inside the star due to energy from previous supernova explosions. Delving deeper into zombie stars may indeed unlock many mysteries about the universe for us. As you know, everything is constantly evolving and stars are no exception. Observing a zombie star is like peeking into the world of a star after its death, which is of great value to our understanding of the life cycle of stars, and even the evolution of the universe. For example, zombie stars can provide us with a unique kind of cosmic timer. Their luminosity tends to decay with a certain regularity, which may be related to the specific circumstances of the supernova explosion and the physical environment inside the star. Therefore, a closer look at zombie stars may provide us with a new way to measure the history of the universe. In addition to this, the existence of zombie stars also reveals to us that there is a state of matter in the universe that we do not yet fully understand. The density of matter in zombie stars is extremely high, greatly exceeding the density of any matter that can be made on Earth. This means that inside a zombie star, matter may exist in a form that we have not yet seen. This is like a mystery hanging in the universe waiting to be solved. Achter space-time vortex. Let me paint you a picture of the space-time vortex. You know, when we talk about the universe, we usually think of a three-dimensional space and time flowing like a river. But in Einstein's theory of general relativity, we no longer think of them as separate things, but as one, forming what we call space-time. If you imagine that in this unified space-time, a massive object, such as a planet or a star, is like a heavy ball placed on an open sheet. It would bend the sheet downward, creating a depression. Other smaller objects, suppose a planet, would be attracted to this depression and rotate along the edge of it. In fact, this is what we call gravity. The concept of a space-time vortex builds on this. If we imagine this heavy ball as a rotating body, such as the Earth or the Sun, It will not only press the sheet down to form the depression, but will also cause the entire sheet to twist as it rotates. This is the nature of the space-time vortex. You can imagine stirring your coffee in your coffee cup, and the coffee will form a vortex, and this vortex is actually a very graphic model of a space-time vortex. That said, the idea sounds quite counterintuitive at first, but think about the broader context of our modern physics and you'll realize that it's actually quite reasonable. In the world of quantum mechanics, particles can dance everywhere, so why can't our cosmic set, space-time, have a bit of a dynamic flavor? Let's take another example. The Earth revolves around the Sun, and its gravity leaves a gravitational footprint in the zigzagging space-time, a trajectory that is akin to the ripples left by a surfer in the waves of the ocean. The Earth continues to roll in these ripples, causing space-time to be constantly pulled and fricted, which in turn creates vortices. So why is it said that space-time can warp or form vortices? Simply put, it is the mass and energy pulling dancers spinning recklessly in it, leaving behind dynamic, vortex-like traces. Well, now that we've talked about it, let's go deeper into the story of Einstein's prediction of the space-time vortex, as if it were a mystery. Think about how cool it must have been for a scientist to sit at his desk with the tip of his pen flying across the page and actually predict mind-boggling phenomena in the universe. Einstein gave us a whole new set of glasses to understand the universe when he came up with the theory of general relativity in the early 20th century. He said that space-time in our universe is not static, but can be bent, like an elastic film. This idea of his was nothing short of a revolution in physics. In his theory, Einstein made a bold assumption that gravity is no longer two objects attracting each other through a mysterious force, as described in Newtonian mechanics, but rather the existence of an object causes the surrounding space-time to bend, and other objects move in this bent space-time. As we mentioned before, a heavy ball on a bed sheet creates a depression. This depression is the curvature of space-time, and the ball moves as if it were rolling on this depressed bed sheet. As an example, let's say that the Earth doesn't just lie still and revolve around the Sun in the depression in space-time created by the Sun, but its own motion too creates a dynamic distortion, a vortex, in the surrounding space-time. The genius of Einstein was that he predicted all this through purely mathematical formulas and physical principles. In his theory, space-time and matter interact with each other. In fact, this effect is very difficult to observe in our daily life because it requires huge mass and high-speed rotation. However, in strong gravitational fields such as black holes, neutron stars, or our planet Earth, scientific experiments in recent years, such as the Gravity Probe B and LEGIO satellites, have measured the subtle effect, verifying Einstein's prediction. Back in 1919, British astronomer Arthur Eddington also confirmed Einstein's theory. During an observation during a total solar eclipse, he noticed starlight bending as it passed near the Sun, which is direct evidence that gravity warps space-time. Just like when you throw a rock into a pond, you not only create a vortex, but you also affect the motion of other objects in the pond. Time and space wrap around celestial objects to form vortices, just as water flows around a rolling stone. To continue to expand on this analogy, imagine that the Sun is the center of a giant vortex, and that the Earth and the other planets are like rocks in a garden as they glide through this vortex. This is why the Earth doesn't fly toward the Sun, or somehow out of the solar system, because it is dancing to the rhythm of the space-time vortex. Every planet, every star, and even black holes are like dancers in the universe, and their mass is the rhythm of the dance, leading the bending and flowing of space-time around them. The Sun, for example, has a much greater mass than the Earth, so the vortex of space-time that forms around it is much more pronounced. And black holes, hey, they're the king of the dance in the universe, and their mass is so great that the space-time around them doesn't just bend, it's so deeply recessed that not even light can escape. These space-time vortices have a profound effect on the motion and trajectory of surrounding celestial bodies. Planets around stars, for example, have their orbits formed in the space-time vortices of those stars. The list goes on, not to mention the dynamical interaction of star systems and galaxies, which is even more complex. All of this, while following the framework of general relativity. Let's have a little brush with the hot topic of black holes, which play a very special role in the universe. You know, when a star has enough mass, eventually it collapses into a black hole. At that point, it becomes an extreme example of a space-time vortex around it that is so strong that any matter or radiation, including light, that comes near it is firmly drawn in, like a supervortex in the universe. There are also extreme objects called neutron stars, which do not have the same staggering mass as black holes, but are strong enough to create a strong vortex in the space-time around them. Neutron stars can rotate extremely rapidly, some hundreds of times per second, and such high speeds can also create complex distortions in spacetime around them. Let's explore empirical studies of spacetime vortices. First, let's talk about the progression of planetary orbits. You may wonder what the term progression means. Simply put, it means that a planet rotates slowly in the direction of the long axis of its orbit around the Sun. And Mercury's progression is a classic experimental proof of general relativity. The tiny planet dances through the warped spacetime of the Sun's gravity in a subtly different trajectory than that predicted by Newtonian mechanics. Einstein's theory explains the phenomenon with precision. The gravitational lensing effect, on the other hand, is a complete cosmic magic trick. It's when a gravitational field, such as a massive galaxy, sits between a distant light source and an observer, and it acts as if it's a giant cosmic magnifying glass, bending the passing light and sometimes even creating multiple images of the source. Through gravitational lensing, scientists can observe objects that would otherwise be too faint or too far away to see directly, demonstrating another spectacular aspect of the spacetime vortex. Well, that's it for this installment. Likes and comments welcome, and thanks for watching.